Hey guys, welcome to module number 5 of design of substructures. So this module deals with the topic retaining wall. So the very first question is, what is a retaining wall? So this is a structure which is used to hold soil or earth so as to provide the required stability. Now you can see over the picture here that there is a retaining wall. So this is the retaining wall which is holding off soil on this side. So by holding off this soil, it is preventing the soil from getting into the road over here, right? So this retaining wall is maintaining two different elevations on its either side, right? Now the soil that is being retained by the retaining wall is known by the name of backfill. Okay. Now let us look at the types of retaining wall. Although there are many types, here I will be discussing only three types of retaining wall. The very first is gravity retaining wall. So these walls are made up of stone, brick or concrete, and these retaining walls are heavy enough to provide the required stability. Okay. An important point is the height of such walls is always less than 6 meters. The other wall is cantilever retaining wall. So from the name only you can make out that these walls make use of cantilever action. Now as you can see over the figure, this is called the stem of the cantilever wall. This is the heel slab and this part is called the toe slab. Now what is a heel slab? The heel slab is the one which will hold the backfill. So here I will be having the backfill, and on the toe slab I will be having the natural ground surface. So I can have a road over here, or I can have any kind of natural topographical features, right? An important point is the height of cantilever retaining walls range between 5 meter to 7 meter. The next type is counterfort retaining wall. So these are very similar to cantilever retaining walls, but these are used when the cantilever is very long. Okay. So to provide stability to the cantilever, we use certain structures called counterforts. So these are counterforts. So counterforts actually tie the heel slab to the stem, and as a result of which an additional stability is being provided. Now the height of such walls are always greater than 7 meters. Okay. Next, let us see how to do the proportioning of a retaining wall. By proportioning, I mean how to fix the sizes of retaining wall. So first we will be looking at gravity retaining wall. So this is the figure of a gravity retaining wall where the height of the backfill is denoted by h. So here I have got the backfill. Now you can see that the top width should not be less than 200 millimeters. It should be always greater than 200 millimeters. The bottom width is in the range of 0.5 to 0.7 h. That means the bottom width should be 50% to 70% of the height of backfill. Okay. And this df denotes the height of the soil near the toe slab. Okay. Here I have got certain projections. So this is the projection over here, which is of 150 millimeter, and here the thickness is denoted by h by 8 to h by 5. An important thing is the resultant forces should lie 1/3 of the base. Suppose this is the weight of the retaining wall denoted by W. Now if I divide the base into three parts, this is part 1, this is part 2, and this is part 3. So the weight or the resultant force should always lie within the middle third. So this is the first third, this is the second third, this is the third number of third. So this is the middle third. So you can see that the weight is lying in the middle third of the base, right? Now let us look at the proportioning of cantilever retaining wall. So in a cantilever retaining wall, the top width should be again greater than 200 millimeters. The bottom of the stem should lie in the range of h by 12 to h by 10, where h is the height of the backfill. Backfill is on this side. Then this is the width of the bottom denoted by capital B. The projection of the toe slab is given by m into b, and the thickness of the slab is given by h by 12 to h by 10. Okay. Now let us see how to calculate B and M. So B is given by 0.95 into H into square root of Ka divided by 1 minus m into 1 plus 3m. So H, I have already told you, is the height of the backfill. Ka is the coefficient of active earth pressure, and m is a parameter. So what is m? Here you can see m is given by 1 minus 4 by 9 beta. So again, what is beta? Beta is gamma into H minus T divided by QA. So gamma is actually density of the soil, H is again the height of the backfill, T is thickness of the slab, and QA is the allowable bearing pressure of the soil. So if I know M and if I know B, I can calculate the projection of the toe slab, and if I know B, obviously I know the bottom width of the wall. Okay, so this is how I do the proportioning of a cantilever retaining wall. Now when it comes to counter for retaining wall, all the parameters remain same as that of the cantilever retaining wall, but here an additional thing that is to be calculated is the spacing between the counter force. So the spacing between the counter force is denoted by L, and how do we calculate L? It is given by L square, which is equal to 11.8 into square root of H by gamma, where H is height of the backfill and gamma is unit weight of the soil. Okay. Now let us look what are the forces acting on a retaining wall. So this is a figure of a cantilever retaining wall. So as you can see on the right hand side, I have got something called PA. So PA is actually the active earth pressure. So this active earth pressure is exerted by the backfill soil onto the retaining wall. This soil has also got a weight of its own, which is denoted by W, and it is acting in the downward direction. The soil near the toe slab will be exerting a passive pressure, passive active earth pressure, which is denoted by PP. Now this passive active earth pressure is very less as compared to the active earth pressure, because the amount of soil on the toe slab is very less, right? Now the soil below the cantilever retaining wall will be exerting an upward reaction, because of which we will be having a upward pressure acting on the retaining wall. Now because of these forces, the cantilever wall tries to deflect somewhat like this. You see, here I have got active earth pressure, so it will try to push the cantilever wall. So the wall will assume this kind of shape, the shape denoted by dotted lines. So this is the shape due to active earth pressure. Now I have also told you that this soil, the backfill soil, will exert a downward pressure, because of which the hill slab will now tend to deflect downwards, right? So you can see it has deflected downwards. Now on the toe slab there is no soil over here, so there will be no deflection in the downward direction, but I have told you that there was a upward reaction. So this upward reaction will now act on the toe slab, and as a result of which the toe slab will be lifted upwards. So from this diagram you can see that this portion is actually in tension. Okay, similarly this portion is again in tension, and again in the toe slab this region is in tension. So we know that concrete is weak in tension and strong in compression. So the areas of my retaining wall where there is tension, I need to provide reinforcement for such areas. Okay, so in the next diagram you can see that I have provided reinforcement primarily on those sites where I found that tension was prevalent. So here I had tension, so I am providing a reinforcement over here. Again hill slab, it deflected down, so here I had tension, so I am providing a reinforcement here, and here in the toe slab it was lifted upwards, so again I am providing a reinforcement at the bottom. So this is how my reinforcements are provided in a retaining wall. So now because of this pressures acting on the retaining wall, I can draw the stress diagram or pressure diagram. See, this is a very complicated diagram, but let me make it easier for you. You see, here I have got the backfill soil. So the backfill soil is exerting a active earth pressure. So active earth pressure diagram you have learnt in geotechnical engineering. It is a triangular shape. So this is the active earth pressure diagram over here, okay, which is denoted by PA, and the resultant force will act at a height of h by 3 from the bottom, something you have learnt in 7th semester. Now if you look to the soil on the toe slab, this is exerting a passive earth pressure. So this is the diagram for passive earth pressure, okay. And at the bottom I have got a uplift pressure diagram. So from the earlier diagram you saw that the toe slab was lifted upwards, right? So here I will be having the maximum amount of uplift pressure, and hence this is what is being drawn over here. The uplift pressure is high on the toe side as compared to the hill slide, okay. So these are the three stress diagrams that you need to draw in a retaining wall. Now let us look at the different kinds of failures in a retaining wall. The first is sliding failure. You see, uh, here I have got my backfill soil. So the backfill soil is exerting a active earth pressure which is acting in this direction. So if this orange color retaining wall is the original position, then because of this active earth pressure it may slide to a different position, say this one. This is the new position due to sliding force. Now this sliding force is actually prevented or resisted by a frictional force acting at the bottom, okay. So this is the sliding force acting at the bottom which will counteract the active earth force or the disturbing force, okay. So this is how sliding failure takes place. Now if my resisting force or the frictional force is not large enough, then the retaining wall will ultimately slide and I will be having a sliding failure, okay. Next is overturning failure. Now you see, the force due to active earth pressure will be exerting a moment in the anti-clockwise direction. So if this is the force, it is at a height of say h from the bottom, okay. So because of this height and this force, a moment will be generated somewhere over here. So this is acting in the counterclockwise direction, because of which the retaining wall will be overturned. So orange color is the original position and this is the new position. So you can see it is lifted about this point, it is overturned about this point. So the overturning is actually prevented by another moment which is known as resisting moment, which we will deal in the upcoming sections, okay. So having known the different kinds of failures in a retaining wall, let us try to calculate the factor of safety for sliding as well as for overturning. First let us see the factor of safety against sliding in a gravity wall. So factor of safety is given by horizontal resistance divided by horizontal force, okay. Let us first see what is the horizontal force. So now if you look into this diagram, the horizontal force that is acting is the active earth pressure force, which is denoted by PA. So in place of horizontal force I have written PA. And what is the horizontal resistance? I have already told you that the resistance is provided by the frictional force which is acting at the bottom. So here I will be having a horizontal frictional resistance force. Now you know that frictional force is calculated by F, which is mu into N. So what is mu? Mu is coefficient of friction and N is the normal force due to the load of the body or due to the weight of the body. Now in our case, mu is the coefficient of friction, right? And what is the normal load? It is the weight of the wall that is acting downwards. So frictional resistance or frictional force will be mu into WW. So the overall factor of safety is somewhat of this term. Now factor of safety for sliding should be always greater than 1.5 if the soil is cohesionless, and it should be always greater than 2 when the soil is cohesive. Okay. Now let us see the factor of safety against sliding in case of a cantilever retaining wall. So in cantilever retaining wall, the forces are quite same to gravity wall, except that here I have got the weight of the soil. Anyway, let us see from the first. The first is horizontal resistance divided by horizontal force. Let us first see what is the horizontal force. The horizontal force is the active earth pressure force, so which is PA. Now comes the horizontal resistance, which will be again the frictional force acting at the bottom, right? So frictional force is mu into normal force. So what is the normal force now? I will be having two forces. One is the weight of the wall, which is WW, and the other is weight of the soil, which is denoted by WS. So the overall frictional force will be mu into WW plus WS. So the overall factor of safety is mu into WW plus WS divided by PA. So just as similar to the gravity wall, factor of safety should be always greater than 1.5 if the soil is cohesionless and greater than 2 if it is a cohesive soil. Now sometimes it is found that the frictional force is not enough to resist the active earth pressure force. So in certain cases an additional structure is provided beneath the wall, which we call as key. So this you can see it's a trapezoidal structure which is provided just beneath the cantilever retaining wall, so as to increase the contact surface area with the soil. Now when the contact surface area is increased, the frictional force is also increased. Okay, so this is how key is used to increase the frictional resistance. Next, let us see the factor of safety against overturning. So first we will be looking at the gravity wall. So if you look into this diagram, I have got two forces. One is the active earth pressure force and the other is the weight of the wall. Now factor of safety against overturning is given by stabilizing moment divided by overturning moment. So overturning moment is actually the disturbing moment or the moment which will cause the overturning of the retaining wall. So in this case, overturning moment will be because of the active earth pressure. And how do I calculate that moment? It will be PA into the height from the bottom. So PA into H1 will be the disturbing moment or overturning moment. So this is what I have written at the denominator, that is PA into H1. And what will be the stabilizing moment? Stabilizing moment will be because of the weight of the wall. So the weight of the wall is WW and the distance from this point is x1. So you know that the active earth pressure will overturn the wall at this point. Okay, and so the moment will be somewhat acting in the anti-clockwise direction. Now the weight of the wall will exert a moment about the same point in the clockwise direction. Okay, so it is acting in the opposite direction, and as a result of which it is neutralizing the overturning moment. So this is how I calculate the factor of safety for gravity wall. So ultimately factor of safety is WW, that is weight of the wall, into x1 divided by PA into H1. Next, let us see the factor of safety for overturning in case of a cantilever wall. So again, stabilizing moment by overturning moment. So what is the overturning moment over here? It is PA into H1, which will be again acting in the anti-clockwise direction. And what is the stabilizing moment? I will be having two types of stabilizing moment. One is WW into x1 about this point, right? WW is weight of the wall, and the other resisting moment will be because of the weight of the soil itself, which is WS into x2. Okay, so this is what I have written at the numerator. So if you see this, this is the factor of safety of overturning for a cantilever retaining wall. Now factor of safety for overturning in cantilever wall as well as for gravity wall should be always greater than 1.5 if your soil is cohesionless, and it should be greater than 2 if the soil is cohesive in nature. Okay, so that's all for module number 5. So in our next video we will be discussing module number 6. Thank you.